Large language models, LLMs, I mean, they just keep getting better, don't they? Doing all sorts of things. Poetry, answering questions, even writing code. But, when you ask them to really reason through something complex like multi-step maths problems or tricky code debugging, that's often where they seem to hit a wall. It's not just about the final answer. It's about the actual thinking process, the journey to get there. And that's the core challenge we're really digging into today. How do we help these LLMs explore all the possible solution paths effectively? How do they learn from mistakes without just getting totally lost? Because standard reinforcement learning, RL, well, it often struggles. Exploration can be unstable, and figuring out which specific step in a long chain deserves credit or blame, that's really tough. Imagine teaching, I don't know, a robot to bake a complex cake. If it burns, how do you pinpoint the exact mistake among 50 steps? Too much flour, oven too hot. It's hard, and relying only on that final correct or incorrect signal, that's a common pitfall. It just doesn't give the model the granular feedback it needs, doesn't tell it where it went wrong or even what it did right along the way.
Right.
This can lead to models sort of overthinking, getting stuck in loops, not making real progress. So the big question is, how do you coach this brilliant AI that keeps getting tripped up? And that brings us to FR3E First Return, Entropy-Eliciting Explore. It's a really novel framework, kind of a fresh playbook for this problem. It aims to help LLMs navigate these huge decision spaces much more intelligently.
It really is a fundamental challenge in LLM-RL, this issue of granular credit assignment.
Hmm.
It's central. Many current methods, take GRPO, for example, group relative policy optimization. They try to estimate the value of all intermediate steps based only on that final outcome.
Ah, okay.
But that just averages everything out, right? It
Yeah.
misses which steps were truly crucial and which were maybe less important, like you said, judging the cake, not the baking process.
Yeah, that makes sense.
Then you've got the value model approaches, PPO, VAPO, things like that. The problem there is training a stable, accurate critic model for the massive state space of an LLM. It's computationally very difficult.
Right.
And it's prone to instability bias. Even with techniques like GAE, generalized advantage estimation, trying to smooth things out, getting those rewards propagated way back to early steps in a long sequence, still really problematic.
So it's like trying to predict every ripple from a stone thrown far away.
Kinda, yeah.
Yeah.
And then there are other methods using sampling or heuristics, VinePeople, process reward models, Prime.
Yeah.
But they all have their own drawbacks. Maybe the heuristic isn't great, or there's too much variance in the sampling, or costs a lot to label things explicitly, or the rewards you derive implicitly just aren't fine-grained enough.
Okay.
So they often wrestle with complexity, instability, costs, or they rely on these brittle rules that just don't adapt well.
So a real uphill battle. How does FR3E start to cut through all that complexity then? You mentioned it rethinks the whole game. The key thing seems to be identifying these high uncertainty points within correct solutions, right? Instead of just rolling out from the start. How does that change things?
That's exactly the core idea. Instead of full rollouts from the initial prompt, FR3E zeroes in on these high-entropy tokens, the points of maximum uncertainty, but specifically within trajectories that already led to a correct answer.
Ah, okay. So it learns from success, but focuses on the tricky parts within that success.
Precisely. From those uncertain points, it then performs targeted rollouts. This constructs what the paper calls semantically grounded intermediate feedback. It actively creates new evaluation points without needing some pre-existing reward signal or trying to do that difficult credit assignment over the whole long sequence.
So it's generating its own feedback, focused right where the model was unsure.
Yes, and it provides this focused guidance without needing dense, explicit supervision. And these synthesized signals, they're particularly useful for guiding the reasoning early on, where things are often most ambiguous. Plus, a huge advantage is its value model-free design. It completely sidesteps those stability issues we talked about with training critic models.
And I read it builds on this principle from Go Explore. First return, then explore. How does that apply here?
Right, it adapts that idea for sequential generation. Go Explore aimed to first find any path to a novel state, and then explore deeply from there. FR3E does something similar. It uses a successful trajectory, the return part, to find these uncertain novel states, these high entropy points, and then launches targeted exploration from those specific points.
Got it. So let's unpack how FR3E actually works. You mentioned two phases.
Yes, two complementary phases that work together. Phase one is first return identifying uncertainty signals. It starts simply, generate a base reasoning trajectory from the input query. Just let the model solve the problem once. Then, it calculates the entropy for each token generated. Remember, high entropy means high uncertainty at that decision point. Like the model wasn't sure which word or number to output next.
Like a writer pausing, considering different words.
Exactly like that. FR3E finds the moments of highest hesitation, the top K highest entropy tokens across the whole trajectory. These are marked as critical junctures, natural forks in the road. These high entropy points then act as breakpoints. They segment the successful trajectory into semantically meaningful blocks. And this defines intermediate reasoning states, basically, snapshots of the reasoning process up to each point of uncertainty.
So it's creating checkpoints based on where the model struggled, even within a correct answer? That's clever.
It is. It helps focus the learning. Then comes phase 2, Entropy-Eliciting Explore diversified path sampling from anchors. For each of those intermediate states, those checkpoints we just defined, FR3E essentially resets the context back to that point. And from there, it generates multiple different ways to continue the reasoning, diverse rollouts.
Trying out alternative paths from the uncertain point.
Exactly. And each of these alternative rollouts gets a simple binary reward. 1, if it ultimately leads to a correct final answer, 0 if not. Then the empirical value of that intermediate state is just the average reward across all those diverse rollouts starting from it. It quantifies how good that reasoning prefix actually is on average.
Okay, so it's exploring locally around points of uncertainty.
Right, promoting diversity but keeping it semantically connected to the original successful path.
Now, something else that caught my eye was this adaptive advantage modulation. That sounds interesting. How does that work?
Ah, yes. That's a neat mechanism for fine-tuning the learning signal. It dynamically scales the signal based on how much the estimated value improves from one intermediate state to the next. So if the reasoning quality seems to be improving significantly as it moves from state SJ to state SJ plus 1, it actually reduces the learning signal slightly.
Reduces it. Why?
To prevent the model from converging too quickly. It preserves exploration, stops it from just locking onto the first seemingly good path it finds.
Okay, so it encourages continued searching even if things look good.
Right. But conversely, if the quality stagnates or even degrades between states, it amplifies the signal.
Pushing it harder to explore more aggressively when it's stuck or going backwards.
Exactly. You can think of it as a kind of built-in wisdom. It pushes harder when lost, eases off when the path is clear. This helps keep the advantage estimate stable and centered around 0, which is important for effective policy updates.
Makes sense. And there were a couple of supporting mechanisms mentioned too. Rejection sampling and clip hire.
Yes, crucial supporting parts. First, rejection sampling. Sometimes a prompt might always lead to the same outcome. Maybe the model always gets it right or always gets it wrong.
Okay.
If that happens, all the rollouts have the same reward and the advantage estimate becomes 0. You get vanishing gradients, no signal for the model to learn from.
So it learns nothing from those cases.
Right. So FR3E uses rejection sampling. If all rollouts for a prompt give the same reward, that prompt is just discarded from the current training batch. It's deemed uninformative.
Ensuring it only learns from cases where there's actually some variation, some signal to follow.
Precisely. It ensures the entropy finding process works on diverse, informative trajectories. Like a teacher focusing on the tests that show where improvement is needed, not just the perfect scores or total failures.
And clip higher.
Right. Standard RL often clips the policy updates symmetrically. This can accidentally suppress the probability growth of tokens that seem unlikely but might be part of a good unexplored path. It can lead to entropy collapse.
The model gets too confident too quickly, stops exploring.
Yeah, like an artist sticking to only one style because it worked once. Clip higher replaces that symmetric clipping with asymmetric bounds specifically between 0.22 and 0.28 in the paper's experiments. This explicitly allows larger increases in the probability of these underexplored paths while still limiting aggressive decreases. It encourages exploring less probable routes without destabilizing the training.
Okay, so a very structured approach overall. After all that clever design, how did FR3E actually stack up? You mentioned experiments on math benchmarks like AME24, GSM-8K, comparing it mainly against GRPO++A. What did they find?
The results were quite compelling, yeah. First off, they saw improved training stability and reasoning capability. FR3E consistently kept higher entropy levels, especially later in training.
Meaning it kept exploring longer, didn't suffer that entropy collapse.
Exactly. It suggests it preserves that exploration capacity, which is really important for complex tasks. On one model, Quen 2.5 Math 7b, the entropy actually started to increase again in later stages with FR3E, whereas GRPO++ just converged quickly to low entropy.
Interesting, so it keeps adapting.
Second, higher performance and scalability. FR3E generally outperformed GRPO++ on the benchmarks, This was especially noticeable for the larger general-purpose models like Qwen 2.57b and Qwen 2.532b.
So it helps push the ceiling for bigger models?
It seems to allow them to leverage their capacity more effectively, yes. Third, more robust positive signals and trajectory consistency. FR3E significantly boosted the number of all-right trajectories, fully correct reasoning from start to finish. And at the same time, it suppressed the all-wrong ones. So it's guiding the policy toward generating consistently high-quality reasoning paths. The biggest model, the 32B, showed this most strongly.
Getting it right more often and more consistently.
Fourth, stable learning dynamics. Looking at visualizations like heat maps over training, FR3E showed a smoother, more consistent transition from low accuracy to high accuracy. It suggests a stable, progressive improvement. Once it learns how to solve a type of problem, it reliably produces correct reasoning chains without big dips or fluctuations. It sort of locks in the knowledge effectively.
That sounds promising.
And finally, there was an impact on response length, particularly for the specialized math model, Qwen 2.5 Math 7BB. FR3E's approach seemed better at supporting the longer chains of reasoning needed for complex math problems. Its average response length increased steadily, while GRPO++'s stayed relatively flat.
Though you mentioned the gains were maybe more limited for those domain-specialized models compared to the general-purpose ones.
That's true. While FR3E showed clear benefits, especially for the general models, the improvements on the already specialized Qwen 2.5 Math 7B were less pronounced compared to GRPO++ problem.
Suggesting that maybe how you train needs to align carefully with how specialized the model already is.
It does suggest that, yes. A specialized model might already have strong internal priors or reasoning patterns, and how a new exploration strategy interacts with that probably needs careful consideration. So, to sum it up, FR3E really offers this potent, structured way to enhance exploration for LLMs and RL. By strategically finding those high uncertainty spots in successful paths and then launching targeted exploration from there, it leads to more stable training, more coherent reasoning, and ultimately more correct solutions. It's a practical way forward.
Definitely sounds like a significant step. And it leaves you thinking, this core idea, finding points of high uncertainty and then exploring locally from there. That feels like it has applications beyond just AI, doesn't it? Think about complex problem solving in general, maybe science, or even just personal decisions. Could a structured approach, focusing exploration based on where you feel most uncertain, be more efficient than just trying things randomly? Something to ponder.